The essence of the quantum theory can be demonstrated in the following way. First, we're going to do an experiment with bullets. And we have a machine gunner here that shoots bullets randomly at a steel backdrop that has two slits cut in it here and here. These slits are cut vertically, right? Then the bullets that make it through the slits will arrive at a wood backdrop. And the bullets embed themselves into the wood, and at any time we could go and dig the bullets out and count up the number that arrives at each of the respective locations, right? So we conduct the experiment, and the machine gunner begins to just spray bullets randomly at the slits. And we see that every now and then it'll ricochet off of this slit and come this way. Some will ricochet and come back further this way. Right? Some will go straight through and make it, but we'll see that most of the bullets will arrive somewhere in the middle, immediately back behind the first slit. And this happens all at the same time, right? Like as the person is shooting, you know, one will arrive here, and then one will arrive here, and then one here, and then one here, and then one here. The bullets arrive one at a time, right? Because they are, in fact, fired one at a time. And so we get two bands as we would expect, with a group of bullets behind the first slit and a group of bullets behind the second slit. Okay? So that's it for bullets. Let's move on to water. So we're going to do an experiment with water waves, and these classical experiments will help us to describe and to understand the quantum electronic wave model later, right? Which we'll do in the third case. So we have a cork here, and the cork is bobbing up and down in this vat of water, right? We have the double slits cut into the steel barrier here, and we have on the backdrop, instead of a piece of wood, we've put some tiny little weight scales, each one of them at a different location, and each one of them can measure a weight value, right? A scale value. And so these scales can measure the amount of water that arrives at their backdrop, because if there's a big scale reading, then that means that a large amount of water arrived at that location and exchanged a lot of momentum with it, right? Right? You know, it's real simple. It's just like if you have a lot of water slapping up against a scale, of course that scale reading is going to read much greater than a scale where very little water slapped up against it, right? Okay. So the scale bobs up and down, and we get these water waves progressing out towards the steel barrier, right? And the cork bounces up and down, waves progress out, and then when the waves arrive at the steel barrier, they will diffract through these slits. And we will get two new wave sources like this. And those two new wave sources will interfere with one another. I'm drawing them as best I can. And where the crest from one source coincides with the crest from another source, we will get what we call constructive interference, because these two crests will come together to add up and to give a larger amount of water arriving at this backdrop. But where the trough from one source coincides with the trough from another source, we'll have a very small amount of water arriving at the backdrop. And then where the crest from one source, arrives or coincides with where the crest from one source coincides with the trough from this other source, we'll get an intermediate value of water arriving at the scale wall right back here. And so we'll see in the middle that the crests are lining up here, here, and here. And of course my drawing is not going to be perfect, but if my drawing were perfect, we would see that we would have a large scale reading right in the middle, right, in line with this barrier here, the center line of this barrier right here in the middle. And then where the troughs coincided, right, we see some troughs coinciding there and right here, right, and then again some troughs coinciding right here, but those, remember this is in time lapse, right, so we have to plot where the troughs arrive, when the waves arrive at the backstop, right? When the sum of the two waves, coalescing and interfering with one another, with the result of that interfering duality of waves, those two waves interfering with one another, we need to plot the result here. And we'll get a plot that looks something like that, with the most water arriving in the middle, right? And then less and less water, and then very little water right here, and then more water, and then less and less water, and then more and more water. And so we get something like that. So the scale readings might mean something like this. And 1, 2, 3, 4, 1, 2, 3, 4. Yeah, and then we'll put this one. Of course, you'll have to forgive my artistic ability. Okay, so we see this interference pattern that is due to these two waves interfering with one another, right? So we did an experiment with bullets where we had two bands, and then we did an experiment with waves where we had these water waves interfering with one another and arriving at the scaled backstop, right? Now we're going to do an experiment with electrons. And we have an electron gun here. And the electron gun is basically consists of a tungsten filament, right? Much like the light bulbs in your home. And the electrons are boiled off of that tungsten filament and accelerated through a voltage, so that we have an electron gun here that randomly shoots these electrons towards this steel barrier here that again has two slits cut in it, right? Then in the back we have a photographic film, so that wherever the electrons arrive, they will expose that region of the photographic film, and we can count up and see where most of the exposure occurs, right? We can even see where one electron arrives by looking what region of exposure, like if this little bitty region of exposure of film is exposed right here, well, that's where an electron arrived, right? Okay, so let's go ahead, let's make a prediction, and this is the prediction that was expected, many years ago, because we've come to believe by this time, we're talking early 1900s here, that the electron is a point-like particle, right? Much like the bullets, we would expect, a band of exposure right here and a band of exposure right here, right? So we expect the exposure to be in line with these two slits, where a lot of exposure right here and a lot of exposure right here. So that was what was expected. Let's run the experiment and see what happens. Now, of course, we can't see the electrons because they're so small. All we see is where they arrive, right, at this photographic film back here. So I'm going to conduct the experiment, the thought experiment that we're doing to understand the quantum theory. And I'm going to do it in time-lapse fashion. So I'm going to let one electron go through at a time, and I'm just going to draw on this backdrop where the electrons arrive in time-lapse fashion, right? So initially, we might have an electron arrive right here. And then a little while later, we'll have one right here. And then one will arrive right here. And then another one will arrive right in the middle. And then another one right here, and then right here. And I'm going to speed this up. So we get this strange, first off, we notice that the bands that were expected, right, is not the result that we're coming to see. We're coming to see something that looks like the diffraction pattern that we saw earlier, right? So this is looking more like a wave, right? Where this scale reading plotted the number of water molecules that arrived slapping off the back of the scales, right? Because the number of water molecules is definitely proportional to the amount of actual water that arrives, right? The amount of water, the weight of water is just the weight of the amount of water molecules that are arriving, right? So we have a number of electrons that are arriving here. And if we plot the number of electrons that arrived as a function of distance x, where x is the length of this thing, right? And in both of them it looks something like this. We would get something like this, where there's a lot of them in the middle, with none of them in this region in between, and then more of them, but not as many arrive here as arrive right here, and then very few, if not zero, and then a grouping of them, and then So we'll get something like this. Right? Okay, and then for the bullets, if we were to plot the number that arrived at a given location, we might get something like this. Right? So this is not at all what we expect, right? This is sort of the wow moment, right? Where it's like, what? Why is that? And Erwin Schrodinger, Louis de Broglie predicted that the electron would have a wavelength, that all particles have wavelengths that are associated with them. He predicted it several years before this experiment was ever run, right, which is a remarkable thing. And then Erwin Schrodinger came along later and developed equations for the wave function. And this theory was put forth and compounded and improved upon for years afterwards by Dirac and others, right? By a coalition of physicists. And the theory goes as the following. We're going to do the theory for one electron, right? So one electron is emitted from the gun. But the contention by the theorists is that because we have not observed the electron has a wave of potential where it could possibly be. And that it's not determined where that electron will be, but that it is just a realm of possibility, a wave of possibility, right? Where the electron could be. And that wave of possibility approaches the barrier, right? And it approaches the steel barrier, and that wave of potential, that wave of possibility, diffracts through the two slits. I'm going to draw this as clearly as I can. Right? Now, each of these two new sources are both associated with the same electron, because this wave function from one electron is arriving at the double slit, right? And then diffracting through, and then each of those two new sources, both associated with the same electron, are interfering with one another to give this end result, right, of an interference pattern on the back wall. And the people who put this theory forward said that we cannot determine where any one electron may arrive, but that over an extended amount of time, if the experiment runs for long enough, we can predict the approximation, the probability of where each electron may arrive, right? So this function here, this interference function, could be predicted with a wave function, the absolute square of a wave function, right? By inserting the initial conditions for a Schrodinger wave equation, right? So this is the quantum theory in its essence, and it can be annotated by the following, the results of which can be dictated by the following experiment. Let's take a box, right? And let's throw an electron in that box so the electron is bouncing around, right? And we open up the box and we look in there, and we see it at this position right here, moving in this direction. Question: was the electron right there before we opened the box, right? Well, the theorists contend that the electron wasn't right there before you open the box, right? But before you open the box, that the electron rather had it was a wave of potential, right? It had a wave function, and that it wasn't anywheres, but it was everywhere within the box. And then opening the box and looking, measuring the electron, caused the electron to take a stand and to be right there. But that it wasn't there right before you looked, but that it had a wave of probability of where it could be, right? So this is the kookiness and the bizarreness of the quantum theory, and there will be parts to follow. I'm going to step aside and give you a clear screenshot.